Ever since the Industrial Revolution, robotic arms have been used all across the world. They can work much larger volumes of work in much shorter periods of time. They can work indefinitely, and best of all, they can work for free. We can see the growth of robotic arms in a couple key statistics. The robotic arm market is expected to grow 175% within the next decade. In 2018, 400,000 units were sold, which doubled the amount that was sold 5 years ago. However, there is a problem. Robotic arms are only used by larger corporations, and smaller corporations rarely use the technology. Small businesses make up 97% of all businesses in Canada, and consequently, these small businesses were also hit the hardest by COVID-19, as you can see in this table. So why is it, during this time of desperately needy economical growth, are SMEs refusing to invest in robotic arms? Well, according to the survey directed to 100 random SMEs in Hamilton, 74% felt that robotic arms were too difficult to use, 21% felt that they were too expensive, and only 5% thought that either they didn't need one or had other reasons. So what does this mean? It means that SMEs do want robotic arms in their businesses, but the fact that they are so difficult to use and so expensive are barring them from making this investment. And I believe that it all comes down to programming. See, up to 50% of a robotic arm's cost can come from programming. The SME must hire a technician. They must purchase all the additional hardware. They must find 10 to 12 days of downtime, all of which costs money. Programming is also closely related to ease of use. In fact, programming can be considered as ease of use. This means that how a robot arm is programmed dictates the price and ease of use of the system, which in turn dictates whether or not an SME will make this investment. What then is robot arm programming? Simply put, it is making the robot perform a certain action. Perhaps you want to make it move in a straight line. Perhaps you want to pick up a pencil and move it to a pencil case. Whatever your desired action is, robot arm programming is the process of teaching the robot how to do it. At the core of robot arm programming is coordinate measurement. All of it boils down to, how can I measure the coordinates of where my desired action is? How can I measure the coordinates of my pencil? How can I measure the coordinates of my pencil case? And how can I measure the coordinates in between? So here's my idea. Let's say that we had a rope. This rope has an origin, and it rotates in 2 axes along that origin. If we knew these 2 angles and the length of the rope, we can precisely determine the 3-dimensional coordinates of the tip of the rope. This means that we can program the robot arm by moving the tip of the rope around and changing the coordinates which the robot arm is meant to move to. I call this concept a 3D cursor. As you can see, the coordinates of the tips of the stick can be precisely calculated at all times thanks to the ropes. If we feed these to a robotic arm, it can be programmed to move to these coordinates. After the concept was developed and the prototype built, it was time to test. I developed a 5-axis robotic arm with a known value of accuracy, this would come into play later, and tested the accuracy and repeatability of the system with this apparatus. I tested the accuracy of each axis with the use of a dial gauge. The 3D cursor was pressed into it, and the data was recorded. Then, the robot arm moved to the coordinates measured by the 3D cursor, and the dial value was recorded again. This was repeated for all 3 axes and can be shown in these pictures. Once these values were analyzed and the accuracy and the precision calculated, I was able to see the impact of my 3D cursor. My system had an accuracy of 0.809 millimeters, a repeatability of 1.309 millimeters, and a cost of $209. This means that the price of programming can be reduced by 97%, all while accuracy remains reasonably high. However, I believe that the biggest improvement that my system brings is the ease of use. The 3D cursor is extremely intuitive to use because it allows the user to physically move the cursor around while programming the robot. Compared against teaching pendants, used to currently program 90% of all robots, it is so much more easy and more intuitive to use. Think of it like this. The 3D cursor is like writing with a pencil, and the teaching pendant is like moving the pencil around by pressing buttons. A paragraph can be written by both, but the paragraph written by the latter will take much longer and will be much more difficult to use. These demos will show you just how intuitive and easy to use the 3D cursor is. The 3D cursor can even program a complex shape such as a smiley face with ease. And I was hugely successful. Costs were lowered by 97%, and the process was made extremely easy and intuitive for the user, all the while remaining highly accurate and repeatable. Contrary to this success, there are still many things that can be improved upon my project. For starters, the robotic arm I used was not high accuracy. It had a lot of backlash, which is jiggling, which made it hard for me to judge if the inaccuracies were induced by the 3D cursor itself or the robotic arm. Many parts were 3D printed, which meant that things did not have a high tolerance and could lead to more inaccuracies in my data. This prototype and its successes, however, bring to light the endless possibilities that this offers. I will aim to develop this further by developing a graphical user interface, which I believe will improve just how intuitive the system is. I will explore a different way of testing, seeing if the errors mentioned previously can be corrected. I truly believe this will significantly empower SMEs and consequently improve Canadian economy for the better, especially in the wake of the COVID-19 pandemic. Thank you for your consideration of my project.